Hello dear students, this is NK. I welcome you all to the Maths Vibes. Here in this channel I am going to teach you class 10 mathematics of NCERT. And the first chapter is real numbers. Here we do Euclid's division lemma, which is the first theorem of this book. And the next is fundamental theorem of arithmetic, right? So in class 9 we studied irrational numbers, right? We introduce irrational number. Here in class 10 we revisit it, okay? Revisiting irrational numbers. We also revisit rational numbers and their decimal expansion, okay? This is quite easy chapter as compared to others, right? And the name of the chapter is real numbers. To study real numbers, let us revise some of the numbers like natural numbers, the counting numbers. Okay, we do it like 1 2 3 and goes up to infinity. Okay, this is all these numbers are natural numbers, right? And if we include 0 in this, we get the whole numbers, right? So we denote the natural number by capital N, and if we include 0 in n, we get the whole numbers. So next is the integers. We denote it by capital Z, right? So all the counting numbers, positive and negative counting numbers, okay, like 1 2 3 and goes up to infinity, and -1 -2 -3 and goes up to minus infinity, and 0, all these are integers, okay? And the next is the rational number. We denote it by capital Q, and the numbers which are in the form of p by q, where q is not equal to 0. So these type of numbers are rational number. For example, 0.23 bar. We can write these type of number in the form of p by q, where q is not equal to 0. Okay, let us take another example like 2 by 7. Okay, so this is also in the form of p by q, right, where 7 is not equal to 0. So these type of numbers are rational numbers. Okay, so next numbers are real numbers, the numbers which we can find on a number line. Okay, this is the number line 0 1 2 3 and it goes up to infinity. Similarly, on the left hand side it goes up to minus infinity. Okay, so the numbers 2 by 7, 0.23 bar, numbers like √2, which is an irrational number and also a real number, right? So we can find all these type of numbers on a number line. For example, let us take √2. From 0 to 1, let us take this as 1 unit, okay, and draw a perpendicular which is also of 1 unit, and draw the hypotenuse by using Pythagoras theorem. This is √2, and from here to here this distance is √2, and we can mark it here. This is √2. Okay, any number, irrational number, rational number, integers, any numbers that can be found on a number line. Okay, these type of numbers which we can find on a number line are real numbers. We will learn more about real numbers in this chapter, okay? And the first theorem is Euclid's division lemma, that is theorem 1.1. So to know about Euclid's division lemma, let us take an example. Okay, 5. I take 5 and I can divide 5 by 1. Okay, similarly I can divide 5 by 2, 3, 4 and by 5 itself, right? And if I divide 5 by 1, I can write 5 as 5 is equal to 1 into 5 plus 0, right? And if I divide 5 by 2, I can write 5 as 5 is equal to 2 into 2 plus 1, right? And if I divide 5 by 3, I can write 5 as 5 is equal to 3 into 1 plus 2, right? and if I divide 5 by 4, I can write 5 is equal to 4 into 1 plus 1, right? And if I divide 5 by 5 itself, I can write 5 is equal to 5 into 1 plus 0. Okay, so now here A is equal to 5, B is equal to 3, okay, Q is equal to 1, and R is equal to 2. That means I can write 5 is equal to 3 into 1 plus 2. That means I can write A is equal to BQ plus R. So this is actually the Euclid's division lemma. Now let us learn the meaning of this statement. Okay, here R should be greater than or equal to 0 but less than B. So here in this example, this is equal to 0 but less than 1. Okay, similarly in this example, 1 is the remainder which is greater than 0 but less than 2, right? Similarly in this example, the value of R is equal to 2. This is greater than 0 but less than B, that is 3. So this is Euclid's division lemma. Given positive integer A and B, there exists unique integers Q and R satisfying A is equal to BQ plus R. Let us take another example. Suppose if I take A is equal to 31, okay, and B is equal to 10. If I divide 31 by 10, I can get the remainder 1. Okay, here the value of B is equal to 10 and A is equal to 31, Q is equal to 3, and the remainder R is equal to 1. Okay, here 31 is equal to 10 into 3 plus 1. Okay, so that means A is equal to BQ plus R, which is actually the Euclid's division lemma. We can find the HCF by using Euclid's division lemma. Okay, this is one of the application of Euclid's division lemma. We can find the HCF. Okay, so here is the process to obtain the HCF of two positive integers C and D, where C should be greater than D. Okay, and follow the following steps. The first step is we are finding the HCF of C and D. We need to find two integers Q and R, where C is equal to DQ plus R. This is Euclid's division lemma. If R is equal to 0, then the HCF of C and D is D. If R is not equal to 0, then we need to apply Euclid's division lemma to D and R. Okay, and we continue the process till we get the remainder 0. Okay, now let us take an example. Okay, find the HCF of 5 and 10 by using Euclid's division lemma. So here you need to find the value of C and D, where C should be greater than D. Okay, so here in this example, the value of C is 10 and the value of D is 5, right? So now you need to apply Euclid's division lemma, where we can divide 10 by 5, so we get the remainder 0. Okay, by applying Euclid's division lemma, we can write 10 as 10 is equal to 5 into 2 plus 0. Okay, here the remainder is 0. The value of R is 0. So in the process of finding the HCF by Euclid's division lemma, if the remainder is 0, then the HCF of C and D is D itself, right? So here the value of D is equal to 5. Okay, so that means the HCF of 10 and 5 is 5. Okay, so if I'm not getting the remainder 0 in the first step, let us take another example. Okay, where I'm finding the HCF of 17 and 25. So here the value of C and D. Okay, C should be greater, that means the value of C is 25, okay, and the value of D is 17. So here I have to divide C by D, that means I have to divide 25 by 17 and I get the remainder 8. Okay, so by applying Euclid's division lemma, I can write 25 as 25 is equal to 17 into 1 plus 8, right? Here the value of R, that is 8, is not equal to 0. Okay, that means we have to apply Euclid's division lemma to 17 and 8. Now I have to divide 17 by 8. So here if I divide 17 by 8, I can get the remainder 1. Okay, so I can write 17 is equal to 8 into 2 plus 1. So here also the remainder is not equal to 0. Okay, so now I have to divide 8 by 1, so I get the remainder 0. So finally the remainder is 0, so I can write 8 is equal to 1 into 8 plus 0. So here the value of R is equal to 0. That means this is the end of the process. We have to continue the process till I get the remainder 0. So this means the HCF of 25 and 17 is 1. So this is the process of finding HCF of two integers by using Euclid's division lemma. Now let us consider example 1. Okay, here are two numbers, 4052 and 12576. So this is the bigger number, and you can write the numbers in this way, okay, with Euclid's division lemma. Okay, now here 12,576 is equal to 4052 into 3 plus 420. This 420 is not equal to 0. That means you have to go to other steps by using Euclid's division lemma in this way. Okay, 452 is equal to this, and now here also 272 is not equal to 0. That means you have to go to another step. Okay, in this way 420 is equal to this, and this is also not equal to 0, so you have to go to other step like this. Okay, 272 is equal to this. Here also this is not equal to 0, so you have to go to other steps. So in this way you need to go to the end where you get the remainder 0. Okay, here in this step 4 is not equal to 0. That means you go to other step. Here the remainder is 0. Okay, that means this 4 is the HCF of these two numbers. Did you observe one thing? Here the remainder is 0. That means the HCF of 24 and 4 is 4 itself, right? But the HCF of other numbers like 24 and 124, okay, 124 and 148, 148 and 272. Similarly, other numbers, the HCF is 4 itself, right? So in this way you can go to exercise 1.1 question number 1, where you have to find the HCF by using Euclid's division lemma. Here in these two numbers, 225 is the greater number, right? So you can find the HCF by using Euclid's division lemma. Similarly, you can find the HCF of other numbers as well using the same lemma. Okay, now I am explaining question number 2 of exercise 1.1. Here we can write any positive odd integer of the form 6q plus 1 or 6q plus 3 or 6q plus 5. Okay, so before that let us do example number 2. Okay, so here we can write any positive even integer of the form 2q and any positive odd integer of the form 2q plus 1, where q is some integer. Okay, so here is the question. We know that by the lemma, we can write a is equal to bq plus r, right? Here in this example, the value of b is equal to 2. So let us take a be any positive integer. Okay, that means here in this question b is a 2. That means the remainder should be greater than or equal to 0, right, but less than 2, isn't it? That means the possible remainders are 0 and 1. So by the lemma we can write, okay, therefore a is equal to 2q plus 0, isn't it? This is equals to 2q, which is the even number. If we multiply any number by 2, it will be even number. Or if my remainder is 1, then I can write a is equal to 2q plus 1. Here I am adding 1 to the even number, right? This means this is the odd number. So 2q is the even number, okay, and 2q plus 1, which is the odd integer. Okay, in this way we can prove this. Now let us come to question number 2. Here we are asked to find the odd numbers, which are of the form 6q plus 1. Here the value of b is equal to 6, okay, and these are the forms of the odd numbers. So let's come to prove this. So let a be any positive integer, okay. So here the value of b is equal to 6. So by the lemma, the value of the remainder should be less than 6 but greater than or equal to 0. Therefore the possible remainders are 0, 1, 2, 3, 4 and 5, right? That means a can be written in any of the following forms. That is, here the value of b is equal to 6, isn't it? So a is equal to 6q plus 0 if my remainder is 0. This is equals to 6q. Here I can take the common 2. Then if 3q, if I take 3q is equal to m, this will be 2m. This is the even number, isn't it? Because I multiply m by the even number. So here if my remainder is 1, then I can write 6q plus 1. Here I am adding 1 to the even number. This will be odd. Okay. Similarly, a is equal to 6q plus 2. I can write this as 2m plus 2. This will be the even number. Okay. Similarly, 6q plus 3. Here I am adding 3 to the even number. This will be odd. Okay. And a is equal to 6q plus 4. This is 2m plus 4. This will be even number. Similarly, a is equal to, if my remainder is 5, 6q plus 5 is equal to 2m plus 5. This will be the odd number. So here you can see that 6q plus 1 is the odd number, right? 6q plus 1, here a is equal to 6q plus 1, which is the odd one. So similarly, a is equal to 6q plus 3. This is also the odd number. And the last one, that is a is equal to 6q plus 5, which is the odd number. Sometimes in exam they will replace odd by even, right? That time you can find the even number in the same way, like this. So now I'm solving question number 4. Here is the question. Okay, here you are asked to find the square of the positive integer, which are of the form 3m or 3m plus 1. Okay, so let a be any positive integer. Okay, so here I can write b is equal to 3. So the possible remainders are 0, 1 and 2, right? So by Euclid's division lemma, we can write a is equal to 3q plus 0. Okay, a square is equal to 3 square, taking a square to the both sides because we have asked to find the square of the numbers. So here 9q square. So this is equals to, you can take a 3 as common and 3q square. So this is equals to 3 into m. Okay, here I am taking 3q square is equal to m. Okay, so similarly, if the remainder is 1, then I can write a is equal to 3q plus 1, and taking square to the both side, I can write a square is equal to 3q plus 1 whole square. Okay, so this is equals to, by using a plus b whole square, okay, like this way I can write it, right? So now this is equals to 9q square plus 6q plus 1. Okay, here taking 3 as common, so 3 into 3q square plus 2q, right, plus 1. So this is equals to 3m plus 1. Here I am taking 3q square plus 2q is equal to m. So a square is equal to 3q plus 1. So now if my remainder is 2, then I can write a is equal to 3q plus 2. Okay, taking square to the both sides, a square is equal to 3q plus 2 whole square. Now here I can apply a plus b whole square. Okay, 3q square plus 2 into 3q into 2 plus 2 square. This equals to 9q square plus 12q plus 4. Okay, so this is equals to 9q square plus 12q. I can split 4 into 2 parts, that is 3 plus 1. Okay, so this is equal to, if I take 3 as common, 3 into 3q square plus 4q plus 1 plus 1. Okay, so this is equals to 3 into m plus 1. Here I am taking 3q square plus 4q plus 1 is equal to m, right? So a square is equal to 3m plus 1, right? So in this question we are asked to find the positive integer, square of positive integer. So this is of the form 3m or 3m plus 1. So this is 3m, okay, and this is 3m plus 1, and here is also 3m plus 1. Now let us come to question number 5. Okay, here you are asked to find the cube of any positive integer which are of the form 9m, 9m plus 1, or 9m plus 8. Okay, so here you have to consider, okay, b is equal to 3, because you are cubing the number, isn't it? So a is equal to 3q plus 0 if my remainder is 0. So a cube is equal to 3q cube. So a is equal to 3q plus 1 if my remainder is 1, and 3q plus 2 if my remainder is 2. Okay, you have to take the cube of the numbers and you solve it, you'll get these numbers. Okay, this is the end of the exercise, and I'm leaving question number 3 for you. You do it by yourself. Okay, in next video I'm discussing fundamental theorem of arithmetic. So till then, take care. Goodbye.